Hey, how's it going? I'm the Mathematician, and today we're going to talk about the best way to perform the best method to factor a quadratic expression. There are a lot of ways to factor quadratic expressions. The most commonly taught is the guess and check method, which has us write down every possible factored form based on our first and last terms and FOIL them all out to see which one is correct. Alternatively, you could complete the square or plug your values into the quadratic formula and construct binomials from the results. Or you could even graph the expression, see where your x-intercepts are, and write your factored form based on those. But all of those options have severe drawbacks. The amount of work required to do guess and check increases exponentially as the quadratic gets more complicated, especially if the quadratic turns out to be prime. Graphing requires either a quadratic that happens to have integer roots or a graphing program that can give fractions, and completing the square or using the quadratic formula are a lot of seemingly unrelated work that suddenly lands you at the right answer. Speaking of which, and this is just being pedantic, but none of these are actually methods of factoring. Sure, you end up at the factored form, but guess and check, as the name implies, has us guess at possible answers and check which one is correct. And with completing the square, graphing, and the quadratic formula, we're finding our answers by other means and just plugging those values into a binomial pair. But pushing those options aside, the best way that I've come across is called the AC method, or box method, or diamond method, depending on how we want to draw out one particular step. Fair warning, the next bit is somewhat incomprehensible, but I need to cover the steps in general before we can get to any examples, so bear with me for the next couple minutes, then we can work on some actual problems. To use the AC method, the first thing we want to do, in fact, the first thing you want to do regardless of method being employed, is look for a greatest common factor. If there is one, pull it out to the front, and it'll just chill there for the rest of the problem. Once that's gone, our next step is to identify our a, b, and c from looking at our quadratic as ax squared plus bx plus c. Armed with these numbers, we draw a big X on our page. In the top area of the X, we'll write whatever we get from multiplying our a and c. That's the AC the method is named after. In the bottom section, we want to just put our b coefficient. Now we want to find two numbers that will both add to make what we have in the bottom section and multiply to make what we have in the top section. Now, we could try to go through all the pairs of factors for our top number and see which one adds up right, and that is the way this method is usually taught, but frankly, I think doing it that way is far too prone to error. So instead, let's go the other way. Let's find pairs of numbers that add to make our bottom number and test what they multiply into. There are a couple things we can do to immediately make our search shorter. If our AC is negative, that means one of our mystery numbers is positive and the other is negative, whereas if AC is positive, the numbers we're looking for are both the same sign as B. So, starting with one of our numbers being either positive or negative 1, and the other being whatever's necessary for them to add to B, simply go through pairs of numbers that add to make B, incrementing each of them by 1 until we get to the right pair that multiplies to make AC. Just as a quick example of what I'm talking about here, if our AC is 14 and our B is 9, normally you'd be told to find all the factor pairs of 14, 1 and 14 and 2 and 7, and find which pair adds to make 9. And there's nothing wrong with that, but I just think it's generally simpler to go through pairs of numbers that add to 9 and multiply them together until we get to 14. So I'd start with 1 and 8, multiply them to make 8, see that it's not 14, increment each of them by 1, and try again. 2 and 7 do multiply to make 14, so there we are. Or, let's say our AC is negative 12 and our B is 1. Traditionally, you'd start by finding all three factor pairs of 12, arraying the negatives appropriately for a total of 6 pairs, and adding the pairs together to see which one adds to make 1. I say start at 2 and negative 1, those being the smallest non-zero integer pair that adds to make 1, and increment each number by 1, multiplying the pairs together until we get to the correct pair of 4 and negative 3. Once we have our numbers, and just for notation purposes, let's write them in the two side sections of the big X, we can go back to our original quadratic and start work on actually factoring it. From the work we just did, we know our two numbers add to make B. That means we can split the middle term into two terms, each with coefficients of the two numbers we worked so hard for. From here, it's a matter of factoring by grouping. Focus on the first two terms and find what factor they have in common, factor it out. Move on to the last two terms of the quadratic, factor out what they have in common. If our leading term of a group is negative, we want the factor we pull out to also be negative, regardless of the second term in the group. If the two terms in our group truly have nothing in common, we symbolically factor out a 1, but leave everything the same. And now the step that confuses the most students, even though it's honestly the simplest one. It just looks weird. If we did our AC method correctly, we should have two matching quantities with different values being multiplied on the outside. Since the two quantities are the same, we can now factor those out, leaving us with one copy of the binomial we factored out times a binomial of the values that were being multiplied onto them. Now I know the dry, variable-filled, general explanation is hard to follow. Believe me, it was hard to write and read too. So let's look at some examples. Simple one first. X squared minus x minus 6. One of my old professor's favorite trinomial. No greatest common factor to worry about, so we identify a, b, and c. A is 1, b is negative 1, c is negative 6. Drawing our big X, 1 times negative 6 is negative 6, and we can put our negative 1 in the bottom. So we need two numbers that add to make negative 1 and multiply to make negative 6. I'm sure a lot of you can already jump straight to the answer, but let's go through all the steps here before we get to a harder one and actually need to. Since our b and our ac are both negative, we know that one of our two numbers is negative and the other is positive, and we further know that the negative is the more massive of the two. Going through pairs of numbers that add to make negative 1, to start with a 1, we'd have to partner it with negative 2, but those multiply to make negative 2, meaning they're not the right pair. So we increment each number by 1. 2 and negative 3 still add to make negative 1, and they do multiply to make negative 6, so 2 and negative 3 are the numbers we're looking for. Now, since our a is 1, we can take our 2 and negative 3 and jump straight to the answer of x plus 2 times x minus 3. But again, let's go through all the steps while the numbers are still small. We break our middle term based on our found numbers, giving us x squared plus 2x minus 3x minus 6. Going to factoring by grouping, our first two terms have an x we can factor out. Our second two terms have a common factor of 3, and since the first term in that pair is negative, we'll pull a negative 3 from them. X times x plus 2 minus 3 times x plus 2. Now we have these two mega terms, and since both of them have that common quantity of x plus 2, we can factor that out, and we have the x plus 2 times x minus 3 that we already knew was the answer. Let's try a slightly harder example. 3x squared plus 10x plus 8. Those terms don't have any common factors, so a is 3, b is 10, and c is 8. Draw our big X. Multiplying 3 by 8 gives us 24 for our AC. 10 down there. Since our a, c, and b are both positive, that means the numbers we're looking for are also both positive. So, going through pairs of numbers that add to 10, starting with a 1, starts us at 1 and 9. Multiplying 1 and 9 doesn't give us 24, so increment each of them by 1. Multiplying 2 and 8 doesn't give us 24, so increment each of them by 1. Multiplying 3 and 7 doesn't give us 24, so increment each of them by 1. Multiplying 4 and 6 does give us 24, so those are our two numbers. This time our a isn't 1, so we don't have that shortcut from before and we have to go through the whole process. Splitting the middle term gives us 3x squared plus 4x plus 6x plus 8. Factoring by grouping, the first two terms have an x in common, the last two terms only have a 2 in common. Factoring those out gives us x times 3x plus 4 plus 2 times 3x plus 4. Factoring out the shared 3x plus 4 leaves us at a factored solution of 3x plus 4 times x plus 2. Now let's look at a problem that, I'll warn you ahead of time, could be considered a trick question. 12x squared plus 21x minus 15. First off, this time we do at last have a greatest common factor. 12, 21, and 15 are all multiples of 3, so we can pull that 3 out, and make this 3 times the quantity of 4x squared plus 7x minus 5. That done, the 3 is just going to tag along on the outside and we can focus on the quadratic inside the parentheses. A is 4, b is 7, c is negative 5. After drawing our big X, multiplying 4 by negative 5 gives us negative 20, and 7 goes down below. Since AC is negative, one side number is negative and the other is positive, and since b is positive, that's the sign of the more massive of the two. Starting with a negative 1, we need a positive 8 to add to make 7, but they multiply to make negative 8, which is more than negative 20, so as always, we increment by 1. Negative 2 and 9 still add to make 7, but they multiply to make negative 18, which is still more than negative 20. Incrementing one more time brings us to negative 3 and 10, which still add to make 7, but multiply to make negative 30, which is less than negative 20. Now we have a problem that's not really a problem. Since negative 2 times 9 is too large, and negative 3 times 10 is too small, there is no Goldilocks integer pair in between that actually does add to 7 and multiply to negative 20. And because we now know our two side numbers don't exist, that lets us know this quadratic is prime. So 3 times the quantity of 4x squared plus 7x minus 5 is the fully factored form. Last one, let's do a toughie. 54x squared minus 87x plus 28. Oh boy. Okay, no greatest common factor here either, so identifying our constants. A is 54, B is negative 87, and C is 28. We draw our big X, and, trusting our calculator for a moment, 54 times 28 is 1,512. Since our AC is positive, the numbers we're looking for are both the same sign, and since B is negative, and should also go in the bottom part of this X, that's the shared sign. As usual, I recommend starting from a -1 and pairing it with negative 86 to add to negative 87, but those multiply to just 86. And because that's so far from the 1,512 we're looking for, I'd recommend counting up by tens for a bit. Negative 10 and negative 77 still add to make negative 87, and they multiply to make 770, which still isn't what we want, but it's a lot closer. So, another 10. Negative 20 and negative 67 still add to make negative 87, and multiply to make 1,340. We're getting closer. Negative 30 and negative 57 still add to make negative 87, but these multiply to make 1,710. Too big. We've passed the pair of numbers we want, so let's start walking it back by ones. Negative 29 and negative 58 multiply to make 1,682. Negative 28 and negative 59 multiply to make 1,652. Negative 27 and negative 60 multiply to make 1,620. Negative 26 and negative 61 multiply to make 1,586. Negative 25 and negative 62 multiply to make 1,550. Negative 24 and negative 63 multiply to make 1,512. 1,512! That's the product we have up in our big X. So our two side numbers are negative 24 and negative 63. Going back to our trinomial, we split the middle term, so we have 54x squared minus 24x minus 63x plus 28. Factoring by grouping, our first group has a common factor of 6x, our second group has a common factor of 7, and the first term from our second group, the negative 63, is negative, so we want to factor a negative 7 out of that second group. Pulling those factors out of their groups brings us to 6x times 9x minus 4 minus 7 times 9x minus 4. And once again, we have that shared factor with the quantity 9x minus 4, so factoring it out gives us our final answer of 9x minus 4 times 6x minus 7. And that's the AC method. Or diamond method, or box method, or big X method. Whatever you want to call it, it's the best way to factor quadratics that I know of. And that, at least in my opinion, is the best way to do it. There are some edge cases I didn't go into, like what to do if the coefficients are fractions or if we have more than one variable. So if anyone has any questions about those or any other odd examples you'd like me to cover, or for that matter, if you want me to explain one of the methods I dismissed at the beginning, leave a comment down below, and I'll make a follow-up video to cover any requests that get posted here in a couple months. And I do mean any examples. This is a new channel, so I need to farm engagement. Speaking of which, I understand at this point the algorithm expects me to tell you to like, share, and subscribe. I don't know who this Sharon person is, but be sure to like her. In the meantime, I'm the Mathematician, and my next video is going to be about the single most skipped topic in all of math academia, parametric equations. With how much I learned making this video, hopefully that should take less than the 10 months that this one did.